Okay, section 2.2, we're going to be discussing density curves and a special distribution called a normal distribution. Okay, density curves are how the data is distributed. Often when you have a dot plot or a histogram and we kind of run a curve over top to kind of get a sense of how the shape is, that's what we're referring to when we're talking about density curves. We know they can be skewed. If it's somewhat flat on the top, we call those uniform, or something more even like this, we call that roughly or approximately symmetrical. The important thing that we want to keep in mind when we're talking about density curves is that all of the area under the curve is supposed to total 1 for 100% of the data. Okay, so when we talk about a normal distribution, this is a specific type of density curve. Okay, it is symmetrical, or at least approximately symmetrical. It is unimodal or single peaked, and it is bell-shaped. Okay, it is bell-shaped. So you can see two pictures here below. These are both examples that meet that criteria of symmetry, single peaked, and bell-shaped. These are both normal curves. One thing that distinguishes a normal curve here is they are always described by their mean, which runs right down the very center from that peak there, and the standard deviation. Okay. I will tell you that the standard deviation, if you move out one standard deviation from the mean, that's going to hit right where the curvature or the point of inflection is. Okay, a point of inflection is when a graph changes from being concave down to being concave up. Okay, and you can see in both of these graphs, traveling out what they call one standard deviation from the mean hits right where that curvature changes from concave down to now it's concave up. Okay, every single normal distribution can be described very briefly using this notation right here. Okay, for example, if you see a capital N, that's describing the shape. That means the shape is normal, followed by, it looks like this is a coordinate maybe that you would be used to in algebra if you were going to plot a point, but in fact the first number tells you the mean of the normal distribution, and the second number is telling you the spread, the standard deviation. Okay, the mean of your normal distribution is the very center, and then the standard deviation is the distance from the center, this is what I was mentioning before, to the change in curvature point. That is referred to in calculus as the inflection point. Okay, number 45 on your homework is going to hit on this idea right there. Okay. All right, so normal distributions are something that are going to continually pop up in all sorts of future chapters, but this is where we are first introduced to this idea, okay? And we have something called the empirical rule, or the 68, 95, 99.7 rule, okay? And in essence, this is illustrated by this picture here. A normal distribution with, we'll just say, a mean of mu and a standard deviation of sigma, typically has approximately 68% of your observations fall within one standard deviation on each side of the mean. So you can see here, we're in terms of z-scores here, okay? So we're going to say that a z-score with a mean of 0, if you go out to the right one standard deviation, to the left one standard deviation, see how tall this is? 68% of the data falls in there, okay? Now, if you were to travel out 2 standard deviations on each side of the mean, now we're including more of the area underneath the curve. Now we're including 95% of the data. And if you go out 3 standard deviations on each side of the mean, you have almost included all of the area and all of the observations that are under this curve, except a teensy bit possibly on each tail. they call it roughly 99.7% of the data should be included if you go out 3 standard deviations on each side of the mean. Okay, so we're going to take a look at some examples. We're going to draw some normal distribution curves. We're going to label traveling out standard deviations here. This says the distribution of the Iowa Test of Basic Skills, known as ITBS vocabulary scores, for 7th grade students in Garaway, Indiana, is close to normal. Suppose the distribution is, okay, and then they use this notation. Of course, we know that they're telling us the shape is normal. The average vocabulary score is 6.84 for the group, and the spread, the typical spread, is 1.55. It says here the range is between 0 and 12, and they're asking us to sketch a normal density distribution. So what you're going to do is you're simply going to draw a horizontal line, and then as best you can, a symmetrical bell-shaped curve above that line. Okay? Directly down the center of that curve, you're going to mark the mean, which was 6.84. Okay? Then, as best you can, you're going to eyeball on the right side, traveling down this curve until it feels like you're hitting the point where the curvature is changing from concave down to concave up. I'm just going to say roughly right about there. I'm going to drop down a vertical line. I'm going to do the same thing over here. Sometimes it's hard to draw things perfectly symmetrical. Okay, now the standard deviation is 1.55. So if I add 1.55 to 6.84, I'm going to get 8.39. That's going 1 standard deviation to the right. If I subtract 1.55 from 6.84, then I get down to 5.29. Okay, I'm going to mark off going out 1, 2, and 3 standard deviations from the mean. Now, once you've traveled out 1 standard deviation, you're just going to eyeball that distance, and you're going to mark, if you were to travel that distance again to the right, and that distance again on the left, that would roughly mark out 2 standard deviations. Okay, so now this would be adding another 1.55 and subtracting another 1.55. So I'm going to label this 9.94, 3.74, and finally I'm going to stretch out 1 more standard deviation. We'll just call it there and here. And again with adding 1.55 and subtracting 1.55. Okay, there's my sketch of my normal density curve. It says here, using the empirical rule, what percent, so this is talking about area when they say this, what percent of these vocabulary scores are less than 3.74, okay? Now I know we have our graph up there. I'm not going to draw the whole thing, but I am going to just draw another rough sketch here. I do want to put the mean down the center, and I can see that when it says less than 3.74, it's talking about this part right here, like going out 2 standard deviations to the left of the mean, okay? So what you want to do for this is you want to mark off that, and you want to shade all the area that's less than 3.74, okay? Now let's think about the empirical rule, and I'm going to go ahead here and just mark, since I marked 2 standard deviations to the left, I'm going to mark off 2 standard deviations to the right, okay? Now here's what we know. We know that if you travel 2 standard deviations to the left and 2 standard deviations to the right, that includes 95% of the data, okay? So if we were, remember, everything underneath the curve is 100%, all the data. So if we get rid of this part that I have marked in green here, that would leave us with 5% left over, okay? But this 5% is in this tail here, and it's in this tail over here. So now we need to take that 5%, divide it by 2, and we get 2.5. We get 2.5%, okay? Now, the correct way to label this is when it's asking you for percent. That's another way of asking for the probability, and we're just going to use an X here to represent a random vocabulary score. Okay, the probability that a score is less than 3.74 is 2.5%. Okay, that would be the answer. You would want to include this graph as excellent communication to kind of support that answer. Okay, let's take a look at the next one here. It says, using the empirical rule, what percent of the scores are between 5.29 and 9.94? So again, without drawing all the way out 3 standard deviations, I'm going to do a rough sketch. Every time they ask you one of these questions, you need to have your own graph to kind of go with it here. 1 standard deviation to the left, we said, was 5.29. 1 to the right was 8.39. Now, this says between 5.29, but it says to 9.94. Now, up above, 9.94 was 2 standard deviations to the right, okay? So I'm going to go ahead and mark off over here 2 standard deviations to the right, okay? And I always shade the area that they're asking you for, okay? So we're talking about this area in between. I'm going to go ahead and label my problem here. I'm looking for the probability that x is greater than 5.29 but less than 9.94. Now we're going to need to get creative here. We said with the empirical rule, 68% of the data is 1 standard deviation on each side of the mean. I did not do a very good job of making this symmetrical, I'm sorry. Okay, so I know this is 68%, but I need to figure out what this extra part is here. Okay, so I'm just going to go ahead and show, here's 2 standard deviations to the right. Okay, we know if you go out 2 standard deviations on each side of the mean, that means that, you know, technically that would be going like over here and over here. That includes 95% of the data. So if we do that, 95% of the data, okay, and let's see here. We want to subtract 68%. What this 27% represents is it represents the amount right here that we're interested in and the amount over here that we're actually not interested in. Remember, this is supposed to be perfectly symmetrical. Okay, so if combined, these 2 sections here are 27%. If I want to know just the amount in one section, I would divide that by 2. Okay, so that means this part right here is 13.5%. Okay, so now if I go back and I take the 68% in green plus the 13.5% that's on the right, that gives me a total of 81.5%. Okay, this wasn't the only way to kind of reason through it, but this was one way to use the empirical rule to kind of reason through how to do that problem. Okay. Now, the importance of standardizing, and please keep in mind when it says standardizing, this is referring to z-scores, okay, z-scores, okay? So when we have the standard normal distribution with z-scores, this is absolutely crucial here. Whoops. The mean is always 0, and the standard deviation is always 1. If we're talking about z-scores, okay? So that's what this is. These are z-scores plotted along the x-axis, okay? Now, remember, when you add and subtract a number to all the values in your data set, it affects the mean. When you multiply and divide all the values in your data set, it affects both the mean and the standard deviation, okay? So let me just write that here. When you add and subtract to all the values, it affects the mean, okay? And there's a reason I'm reviewing this, because this is going to be relevant here with what we're going to talk about. When you multiply and divide to all the values, it affects the mean and the standard deviation, okay? So let's say that we were going to take all the values in our data set, okay? Whatever your data set is, you surveyed everybody, you asked them how tall they were, and you wrote it down in inches, okay? And we want to convert all those values into z-scores, okay? How you would convert that into z-scores is you would use this z-score formula. Okay, the x would be you taking each individual value. Now look at what you would do. You would subtract the mean of the data set, and then look what we're doing. We are dividing by the standard deviation, okay? Dividing by the standard deviation, okay? Now, I want to show you why the mean of the z-scores is always a 0, okay? The reason it's always a 0 is because if you were to take this z-score formula here, okay, and you take the mean of your data set, okay, remember, measures of center are affected by both addition and subtraction and multiplication and division. Remember that Fahrenheit Celsius example we had? This is like our formula here. We're converting, and what goes here is what do you want to convert? Well, if we took the mean and we plugged that in here, because we want to convert the mean into a z-score, look at what the formula would be. It would be taking the mean of your data set, and then you'd subtract the mean from it if we're changing it to a z-score, and we would divide by the standard deviation. Well, what you're going to get in the numerator is you're going to get a 0. 0 divided by anything is still 0. This is why the mean of z-scores is always going to be a 0 every single time. Okay? The reason that the standard deviation of z-scores is always a 1 is the same reason. If you took the standard deviation of your set of data and you wanted to use this formula to convert the standard deviation into a z-score, you would plug the standard deviation right in here for your x, okay? So you take your standard deviation. Now remember, when you multiply and divide, it affects standard deviation and mean, center and spread. But if you add and subtract, it only affects measures of center. So if I'm trying to convert a measure of spread, I'm not subtracting this in the formula, okay? I'm only going to do the division, and look what we're dividing by. We're dividing by sigma. So I get sigma divided by sigma, and I end up that the standard deviation of the z-scores, it's always 1. Okay, so this is like the formula you use to transform. This is the transformation if you're going to take all of the original values, but then convert them over here into z-scores. Okay, so you just want to make sure that if we're talking about z-scores, the mean is always 0, the standard deviation is always 1. Okay. All right, I'm going to introduce you to a little bit of the standard normal table, which is found in your formula sheet. Kind of show you a little bit how it works, and we'll dive more into this tomorrow. Okay, the standard normal table is the first table that you're presented with in the stack of formula sheets that you're allowed to use for the test. Okay, and there is a little picture like this at the top of the table, and you'll notice it has things shaded to the left. Okay, and that's very important here. The table entry for each z-score value is always referencing the area under the curve to the left of the z-score. Okay, this area can be referred to as a p-value, which is the probability, the percent of the data, or the proportion of the data. All of those are the same thing. Okay, so I just took a little snippet of this table A, the standard normal z-score table here, to help us with these problems. But I'm going to show you, this is what it looks like in your formula sheet here, okay? It has that graph I was referring to where the area is shaded to the left, and you can see along the left side are z-scores out to the tenths place, and across the top takes you to the hundredths. So I'll show you here with this. Okay, so the question is, all the p-values from the chart are finding the proportion of the data that is to the left of that z-score. Now, very important, when you're calculating these, you need to always draw a curve and have the area shaded that you're wanting to identify. Okay, so let's just look at like 2 of these, and then we'll stop here. Okay, so this wants to know what's the p-value. In other words, the p-value is what's the probability or what proportion or percent of the data would be located on a normal distribution for a z-score of negative, a z-score of negative 2.33. Okay, so I'm going to draw a curve. Okay, we're talking about z-score, so my mean should be 0. Okay, here's one standard deviation. Here's two standard deviations, but this is asking for like 2 1/3 to the left of the mean, negative 2.33. Okay, we're looking for the probability that a z-score is 2.33 standard deviations to the left of the mean or less than that. So I'm shading that little itty bitty amount in the left of the tail. What you would do is you would come up here to your table, and along the left side, you would find the z-score out to the 10th place. Okay, so I see right here, negative 2.3. Okay, then across the top, you're going to do to the 100th place, the 0.03, so that when these two are paired together, they make the number negative 2.33. Okay, you follow it across the row, down the column, that lands you with the area to the left of that z-score is 0.0099. Okay, let's try one more here, and then we'll do several more of these tomorrow. I started drawing some little bell-shaped curves here for you. It says, what proportion of the data falls less than a z-score of 1.56? Okay, so I'm going to mark that the mean is 0 down the middle. Okay, here's one standard deviation to the right. There's 2, and we're looking at a z-score of like 1.56. So I'm going to label where that is. Okay, this said less than, so I'm going to shade everything to the left. Now, this is more than half the curve, so I'm definitely expecting my answer to be more than 50%. Okay, let me clean this off here. Okay, I'm going to find 1.5 along the left. I don't have that here, so I'm going to have to flip to my other table here. Okay, 1.5. There are two graphs. One table is for all the negative z-scores, and the other one is for all the positives. So you're going to look along the left side and find 1.5. See that row, 1.5? Okay, whoops. Oh boy. Okay, there we go, 1.5. And then we want to find 0.06 across the top, and we want to look where those two things collide. I think they're colliding at roughly 0.9406, okay? 0.9406. That means roughly 94.1% of the data is located in that shaded area.